Okay, take it away, Amy.
Okay.
Thank you so much.
Okay, thanks. Thanks so much for having us here to talk about what we studied for the Uranus orbiter and probe during the decadal survey. And the way we've organized this is that Francis and myself will give you an overview of the mission study. Then we're going to go to separate science talks, talking about the different science disciplines and areas that the mission are going to cover. And then we'll come back for a wrap up at the end for questions. So go ahead to the next chart. So you're going to see this chart a lot in a lot of places. This is kind of our elevator pitch of why we need to go to the Uranus system. And it's because we can explore the nearest ice giant system. And this is going to help us to uncover how ice giant sized worlds form in other star systems, as well as in our own solar system. Understanding, in particular for the Uranus system, really the extreme responses that you get in the atmosphere, the moons, the rings, because of the fact that the whole system is tilted on its side. We'll be able to investigate potential ocean worlds, which, 10 years ago, we never would have even thought that you might have them out, I think, at Uranus and that far out in the solar system, but there is some evidence for that. And then, of course, inspiring the next generation of planetary explorers. We've said this time and again throughout the mission study, the brief out, and so on, that this is not my mission or those of us that helped to formulate this mission. This really is for the next generation, because we're talking about long timescales here on getting this mission going. So next chart. Here are some overarching science goals and example questions that are in the study report. But it basically focuses around these same areas that you see throughout the OWL decadal survey. Questions about origins, when and where did Uranus form? Did Uranus and Neptune migrate? Did they swap positions? How did we rearrange that outer solar system? In addition, what tilted Uranus over on its side? Was there a catastrophic giant impact early on that potentially rearranged its interior and gives us the very strange heat budget we have in Uranus? Also, we have these satellites that formed with the planet, so it is the last regular satellite system. But again, that had to happen somewhere in this time frame where we potentially tilted the whole system on its side. In terms of processes, what are the mechanisms transporting heat and energy in the planet today, as well as in the satellites? How do all these components within the Uranian system interact with each other? We have the planets, we have satellites, we have rings, we have an interesting magnetosphere. Interesting solar wind interaction. So there's a lot of complex processes going on in the Uranus system. And then, of course, habitability. Did any of Uranus's moons have oceans in the past, or any of them presently ocean worlds? There's some interesting heat fluxes out there. Okay, next chart. So I'm not going to go through the science traceability in detail, but what you heard from Lori is kind of our takeaway message, that the STM that we came up with during the study is very similar to what you saw in the 2010 decadal report, as well as the studies that were done in 2017 looking at Uranus and Neptune. The key is really that it's a very unexplored system. So the system science is going to be transformative. And the questions really are big, high-level questions that I think are very cross-disciplinary in nature as well. And then the next chart is just the other half of this traceability matrix. And I won't go over this in detail because you're going to get science talks in a few minutes that are going to basically discuss each of these areas. Okay, next chart. So what did the mission look like? The key that we wanted when we designed this was we wanted a mission that closed, it was feasible to do now, and it had a lot of flexibility. And I think that is where we ended up. There's no new technology that's required for this mission. We don't have to rely on any miracles. We're not waiting for anything to be developed. And there's also lots of launch windows and tour options. Now, Lori referred to this as the Cadillac mission, and I would take a little bit of a issue with that. It's not the Cadillac mission. This is a smaller mission than Cassini. It's a smaller payload. We actually tried to be very streamlined in the sense that we didn't put on every possibility because we wanted to make sure we had something that closed. However, if you look at that spacecraft, it is kind of a stretch limo there. It's much more than you need for that small payload. And that's just a function of this was a very fast study in a very short time period. There wasn't time to optimize all these elements. So that sort of thing really can be streamlined quite a bit. The payload can be discussed, but this is a smaller payload than Cassini. The notional concept that we closed with had a flight time of about 11 years, depends which trajectory you choose, and it fits on a Falcon 9 heavy expendable with margin. And so again, we wanted to make sure we had lots of margins on this mission, that we were not driving things really tight in any particular direction. So this particular design delivered 4,200 kilograms to orbit, including the probe, with all your margins, and it left 1,100 kilograms on the launch vehicle. This particular study, the other thing we wanted to make sure we did was to have a complete end-to-end trajectory. So all of our previous studies did not quite do that. They looked at the different parts of the mission piecemeal, rather than completely putting them together. And what happened, if you looked at the 2010 decadal report and in the summary at the end of its potential risks, was that we had orbit insertion happening basically an hour after probe relay. So you had two critical events back to back, with competing desires in terms of being Earth pointed or not, and so on. And that was really pretty uncomfortable. But again, it was the nature of doing these very fast studies. And so one area we chose to focus a lot of energy and attention on was this trajectory. And what we ended up doing was you take the probe into orbit, that separates out your orbit insertion from your probe release and your probe relay. So this now closes your full mission tour, your cruise trajectory to orbit insertion to probe release, and then your orbital moon tour after that. Next chart. So trajectories and launch windows. You've heard a lot about this. What is the optimal launch date? And it is, of course, to launch in 2031 or 2032, because then you get a Jupiter gravity assist. So that does help you get out there faster. It is the most cost-efficient approach, but it's not a showstopper. And so there's lots of good opportunities. We show a bunch of these in the study report that use Venus and Earth flybys. But the key to remember is that there's thousands of options to sort through. And it all depends on what you want to assume for your launch window, what you want to assume for your launch vehicle, which will presumably stay the Falcon 9, but also how long you want to take to get out there, how much fuel you want to get to slow down. So there's a lot of different factors that go into this trajectory trade space. But the key is that although we focused in on those 2031, 2032 launches, there are lots of other options. But there's one other factor in this, and this is how much mass are you bringing into orbit? So this again comes back to that streamlining that spacecraft. How much do we need to put into orbit? Because that also kind of constrains some of these windows. So the next chart shows what I'm talking about. So when we were looking at the study, why did we ended up focusing so hard on those Jupiter windows? And part of that is because we were doing everything at the same time. So we had to have our trajectory decided before we knew our final mass of the spacecraft. So what this shows is a whole bunch of different launch windows with different times of flight, trying to keep the amount of fuel for slowing down to a delta V less than 1.8 kilometers per second. So that's why, you have to, again, decide on this three-dimensional trade space. The dashed lines that I show on here show the masses. And the top line is, using this study, what we were assuming for our post-orbit insertion mass. That's the maximum mass with all those margins on top. The lower line is what the current best estimate was, which again could come down as you refine it. But that's why, you have to kind of make decisions based on these numbers. So if you go forward. So when we were looking at the study, because we were using that maximum mass, we had to be above that dashed line. And so we honed in on the ones that I circled. Next. If you expand it out, really you have a much bigger trade space than that. And again, this is already still making some assumptions. So there's thousands and thousands of opportunities, and we just have to sort them based on all these different parameters. Okay, next. So as the design matures, the likely launch dates are known, then you can refine this down. But just so you know, we are not limited to the 2031 and 2032 launches. Okay, next chart. This is a different way to look at it. Now we're looking at time of flight. Across the bottom, same basic thing. When it depends what you assume for your inserted mass at Uranus, how long you're willing to take to get there, and how much fuel you're willing to expend. Okay, next. And so again, we'll keep refining this as those designs mature and as those technical studies go forward. Okay, next chart. So in terms of the alternatives beyond that 2031-32 flyby, assuming again we stay on that Falcon 9 heavy expendable, we stay with all chemical propulsion. If you want the same mass and arrival speed, then you probably do need to use an intercruise option where you fly by Venus and Earth. That might give you a couple-year penalty, but you can still close the mission with that. Another option, of course, is that lower post-orbit insertion mass. So as you streamline the design, make the spacecraft, again, probably a little bit smaller, as the margins decrease with maturity, that also opens up your trade space. And then the final option is to allow a higher arrival velocity. There's lots of mass margin currently, so you could do a bigger burn. And again, that can buy you back some time and or possibly get rid of some of those gravity assists. So there's thousands of options available. This will refine over time. So there's no showstoppers, in short. So the final mission formulation will optimize all these factors. So this is what we used in our study in terms of our high level mission phases. We had a long interplanetary cruise, about 11 years. Then we did orbit insertion, release the probe on the first apoapse, do the probe relay, and then we work into the science tour after that. I don't think there's anything else really to cover in here. Go to the next chart. This is probably of more interest to people, the concept of operations. The orbit that we got into was a 34-day orbit. It starts in polar orbit just because that's how we approach Uranus, tilted on its side. And we used titania to pump down to an equatorial orbit. Now, Uranus does not have one big moon like Titan or Triton to help drive the tour. So you have to do a lot more flybys of titania basically to crank the orbit down to the equator. But you do get a nice moon tour out of that. We assumed a Ka band science downlink with 1 8-hour pass per day, similar to Cassini. You could do additional passes for critical events as needed. And we assumed that data had standard compression. So we didn't, again, require any miracles on the instruments or the DSN or anything like that. Solar conjunction, not a problem during any critical events. And we looked at 4 different orbit types just to prove to ourselves that we had sufficient downlink that far away to achieve all of our science goals. And so we did a Uranus or rings remote sensing focused orbit that tends to be very data volume intensive, lots of imaging, spectral image cubes, those sorts of things. But then we also looked at fields and particles magnetometry focus, which tends to be much lower data volume. And then the other type would be satellite flybys, where you have intense periods within the orbit, but not as spread around the orbit. And all of these close with sufficient margin on the downlink. Okay, next chart. This is the tour science coverage. So again, you start with a polar orbit and you pump down using titania to get down to the equatorial region. And I believe there were 10 titania flybys, Francis can correct me, before we got down to equatorial. But we did look at the example coverage that we get, and the bottom plot there shows aerial at high spatial resolution and low phase. So we do get good coverage there. We tried to get satellite flybys of all the major satellites at less than 4 kilometers per second. And again, this was just an example tour. So there's lots of flexibility. Tweaks can be put in there for getting very specific imaging of, for example, the rings or other small moons. And it'll depend a lot on the arrival date. And so all of this has a lot of flexibility, but it is at least case in point that we close and we can get down to doing a nice satellite tour. Okay, next chart. So to summarize on where we are in the study, all the mission studies since the last decade have converged on the same general design as Lori was saying, because this gives you really the most science value per dollar. So we describe it as a moderately instrumented orbiter with an atmospheric probe. Kathy Mans will talk about the atmospheric measurements, but a probe is critical. There are some things you cannot do from remote sensing. And so you really do not want to get out to Uranus and not have that probe. The science traceability is very stable. We've been seeing the same types of goals in all these studies. And it comes down to the fact that there's just spectacular system science waiting to be done. This particular study showed that the mission closed with a variety of launch windows, no new technology, critical event timing has all been resolved. So we no longer have 2 events within an hour of each other. And we can get to this orbital tour that precesses down to the equatorial plane. And even without doing any of that streamlining Laurie talked about, the mission closes on the Falcon 9 Heavy with lots of margin. So really the next step would be the pre-formulation studies, the point design optimization, again, looking at much more likely launch windows and constraints, whatever they might be. And then you can look at that trajectory trade space. Francis just put a note in the chat that there were 16 Titania flybys getting down to the equatorial orbit. So this is where you can find that decadal concept study report if you haven't already seen it. It is up on the Decadal Survey webpage. This is basically, I think, a drive that has all the mission studies, but it's in there. So now I want to pivot and go over to doing the science. So the next chart is icy satellites. So I'll turn it over to Paul Schenk for that.